So let's get to it. I tried to bring these terms together, and Destination Earth is a program that Christina has mentioned, which is where this all comes together. It's live. It's a live European project. It's actually funded with quite a lot of money. It's 150 million euros for 2.5 years, and presently it's going into its second phase for about the same money. So overall, it's probably $500 million investment of European taxpayers into this. Okay, and I think that's justified, and I'll try to convince you why. So first, for those people not so much involved in weather and climate, there's no pointer here, no? No. All right, not so much involved in weather and climate, just to explain the differences. So when you do weather forecasting or weather diagnostics, you look at events. You know, the rainfall of tomorrow, the flooding of yesterday, something, it's individual events. When you look at weather regimes, so that's like in between weeks and months ahead, you look like at anomalies. So the next month is going to be warmer than usual, but you don't look at an individual rainfall event, for example, okay? And when you go to climate, then you look at really long-term changes in our climate. You know, are the mid-latitudes or the Mediterranean going to be drier than in the preceding 50 years, or wetter, you know, or will there be more storms? But you are not related to any of the above. You know, that's a bit the difference. Models over time, and you do this with models, obviously. It's simulation models based on first principles of physics. They try to predict what's happening out there based on the best scientific knowledge that we have. You put this on big computers, you run this into the future, and you try to predict what's going to happen. So the complexity of these models has increased over time. You know, in the early days, the models were very simple: ocean atmosphere, then you add ice, and increasingly these models became more and more complex because the Earth is complex. You know, and small scales affect large scales. The Amazon rainforest affects probably the monsoon on the other side somehow. So everything interacts with everything else. And for climate models, you basically have to cover the entire complexity of everything, including ecology, plants, phytoplankton in the ocean, you know, the slow meridional overturning circulation, you know, things like this, ice and stuff. In weather models, we don't need that much complexity because usually the weather that you predict for the next kind of weeks doesn't depend so much on the changes in the Amazon rainforest, but it does depend on atmosphere, ocean, sea ice, atmospheric composition. So there's a difference, but fundamentally the physics principles are the same. And one thing that you might have seen 2 years ago, you know, because of these achievements of the improvements of weather forecasts, the importance of climate prediction for the future, you know, turning our society into something carbon neutral in the future, the extremes that we see with apparent climate change every day, every week, somewhere. You know, the foundation for the climate part has been laid many, many years ago. And this is why the Nobel Prize in Physics was given 2 years ago to Klaus Hasselmann and Suki Manabe for laying the foundation of that, you know, and believing in the physical basis of the modeling, giving us some confidence about what's going to happen in the future. And I think that was really, really a great thing. This is going to be very simple, okay? It looks complex, it's very simple. So what's under the hood of these models? I mentioned it's physics principles. We have equations that we know, which are there. We can solve those, and we do this on grids, so you have like grid points, and the finer the grid is, the better you know, you resolve detail and so forth. So these equations we kind of know. So that's a good thing. And we solve them with numerical methods, and we do this in time steps. So you integrate your forecast into the future, and then you stop at like day 10, let's say, for a weather forecast, or 30 years for a climate forecast. One fundamental issue is that we cannot resolve with infinite detail. We have to approximate or stop somewhere because computationally it becomes otherwise too expensive. So there's a lot of things going on at very small scale that we cannot explicitly simulate. And that's a problem, because in these equations we have these red terms, and it doesn't matter what they're called. They refer to the effects of these small unresolved processes on the large scale. So the climate, or the influence of Rome, the roughness of the buildings, the heating, you know, that you have when you have, you know, a day go by, affects actually a weather system that goes across Rome. But that's not resolved in these models. So there's a fundamental source of uncertainty in these models that gives us trouble. And that's one of the main reasons that we want to overcome, actually. One main weaknesses we want to overcome. That's the main point of this slide. Another important development in our discipline has been the foundation of chaos theory, which actually goes back to this person who wrote a paper in 1963 at Lorenz, which was called Deterministic Non-Periodic Flow. And it simulated with a simple toy model how error grows in a dynamic system. So you try to simulate a dynamical system, like it could be the evolution of a rainforest, or weather, or something else that's highly dynamical, has a lot of free parameters. If you don't know the model or the actual process very well, or the starting conditions, when you initialize the model and then you predict the future for weather, for example, the errors can grow very, very large, very, very quickly. And that's what chaos theory is about. You have the same thing, for example, in markets. You have small perturbation in global markets, a bank collapses somewhere, and then you have knock-on effects that change global economy. Similar thinking. The way this is solved or addressed in weather and climate prediction is that you actually don't run one forecast, you run 50 or 100. And the difference between these 50 and 100 is that you try to represent exactly that uncertainty. I don't know my initial conditions very accurately. I try to bring this in. I know that my model has weaknesses, as I've shown before. I try to represent that in my simulation. So I have 50 different trajectories, like these lines there. And the likely weather in the future is in that space, And the more narrow these lines are, the more confidence I have. The less. In summer, predicting a rainstorm over Rome or, Piazzale Aldo Moro is very uncertain. Now or in winter, if it's very stable, it's very easy. Right. So something we're very concerned with is climate change and how's future weather going to be with climate change. And what you probably hear or read in the papers is this stuff about a 1.5 degree world, 2 degree world, 3 or 4 degree. These are different scenarios that scientists play through with the models, and they say, if we keep emitting carbon dioxide to a certain level, the global change in temperature will be 1.5 or 4, depending on what we do. And the impact on the simulations and what you see there in terms of warming, so the distribution of global heating, of the effects on soil moisture, for example, very important for agriculture, or precipitation are very, very different depending on these different scenarios. So for us, it's very important, of course, to stay as much to the left as possible, to keep these changes as small as possible. Now, the top one, about the temperature, we're very certain about that. The models are very good at predicting this. As you go down and you go into the hydrological cycle, everything related to water, these predictions become more uncertain. But that's a problem, of course. If you want to understand what happens to the Mediterranean in terms of storm frequency that bring the floods to Tuscany and Emilia-Romagna, then we need confidence in this, which we right now don't have in climate models. That's a problem. Oops. Yeah, there's another example. We heard about the AMOC, so the Atlantic Meridional Overturning Circulation. There's a lot of other effects and publications on this, and I can just refer to the previous work, where we know that there's complex processes where how climate can change and what the mechanisms are. And some of these mechanisms are very fickle. Little changes can create dramatic consequences. Again, a chaotic system. I think the term tipping points has been mentioned before. So these are points where where the climate system just flips. For example, if this Gulf Stream, so the transport of warm water towards us, stops, we will have another ice age. When it stops and how it stops is very difficult to simulate, but the consequences will be dramatic. Understanding this is very important. Therefore, we need the accuracy, the understanding of the processes, and then good models to represent that. And then it's important to think further, and this relates back to my initial message of interdisciplinary work. So this is something from a paper in Nature from some time ago, actually, but I really love it. So this is like, at the bottom left, you have like a weather pattern change. You have a certain weather pattern that creates a heat wave and a drought in Europe. And we have seen this a couple of summers now in sequence. So for a couple of weeks, it's too hot and too dry, you know. So you have a lot of impacts of that. Vegetation is stressed, harvests may fail, you may have more forest fires, it has impact on health, it may cause social instability and economic problems. So there's this whole chain reaction of things that can happen if at the beginning something in the physical system changes. So we need to think much further than rainfall and temperature. We need to think everything, so social system, you know, food, health, water, all of this. Just some examples, you know, how important that is. These are 3 different simulations with these 3 different scenarios of temperature. This was published a while ago. And what this paper says, it played through these scenarios and it calculated surface temperature possibilities in the future. And where you have the violet colors, you will have temperatures at which your body cannot sweat enough to cool the body down. Which means in these violet areas you can't live. You can't live outside. You will die and overheat. So imagine this being a real concern in 30, 40, 50 years, that there are certain areas on the globe that just become uninhabitable because our body cannot sustain the heat. Important information. Another one is, let me quick back. So another one, energy. You know, this is wind energy, and this grid there is the grid in which electrical energy gained from wind is injected and distributed. You want to know in the future how to predict what the wind changes are going to be, so that you set up your renewable energy windmills and solar, of course, in an optimal way and manage that system even safely with extremes. So if your wind regime changes and your extremes change, this entire energy system that we rely on today will change. And water extremes, and I picked this latest Italian example, you know, something where, of course, we need to have high confidence in how future extremes are going to change with climate change, which has, of course, locally, as you know better than I, incredible consequences. And sometimes it's not even up to the forecast to be improved, but the response by the authorities. You know, in this case, for example, you have a good 3-day forecast of the event, and then, you know, that should be enough time to save people, but it never does, you know. So, improvements. So this is something we look at in weather forecasts. So we look at how good are we every day, because we predict weather every day, we observe the day after and the day after, so we can verify actually the forecast every day. So we have lots of verification data. So what these curves show is a certain score, it doesn't matter. Better, higher is good, higher is better, okay? This is for rain, this is for something else. And you see that over the last decades, it was always going up, which is good. You know, better observations, better models, because we have better computing, better understanding, all of that. Very good. And the trend curve, it's this dashed line, is about a day a decade, which means like every 10 years, we improve by so much that we can forecast the same event with 1 day more lead time. So the flood that we can predict very well 3 days ahead today, in 10 years we can do 4 days ahead. That's 1 day of gain, of warning time, time for evacuation, things like that. The other thing, coming back to this one here, is, and I mentioned, you know, rainfall distributions in future climates are very much related to extremes and people dying and, you know, flooding and infrastructure being lost and stuff. But we're not very confident in that. So despite everything we invest, it's not good enough. Okay? So we need to accelerate. This is why we came up with a new initiative that actually tries to put all of what's needed together in so-called digital twins. And digital twins combine a couple of things. It's after better quality, so improve all these weaknesses that I was trying to point out, but also bringing in the societal sectors with the physical part, so not stopping at rainfall temperature, but looking at the impact that matter to society and have it in one system because nature doesn't distinguish, we do. Bring it all together in one system, and really importantly, interactivity. And that means access, that a scientific expert like you can actually deal with the system, but also a decision maker, in Europe, in Brussels. You can play with the system, has a much better access to the information, and can go through different action scenarios and trial out solutions. And this is what this means. And we published this like 2 years ago. So this was the beginning of what we call digital twins. So do it better and do it faster. If we have to wait 10 years to get another iteration of climate models, that's too slow. It needs to go faster. So if you could imagine the perfect information system, if you just don't think about anything that we don't know or can't afford or fund, what would you like? Ideally, who knows ChatGPT? 3 people? 4? Or more? Okay. So, people know about ChatGPT. Ideally, you have a system you can talk to. You ask it a question. You say, what's the risk of extreme precip in Italian in the next decades or something? And what should I do? And then you have access to something like this, where you have a hierarchy of interactive levels, where you have the human system, everything that society is about, the physical system. You have unlimited access to data from which you extract the information that you want, which may be for an AMOC scientist different than for a politician. So you can extract that, and then you can derive from that what you really need, if you're a scientist writing a paper or making a decision in the end, There's a level, you have to be able to go up and down, and ideally this comes for free. So you really want to interact with all these levels, and you want that to be fast, and don't wait for it for five years or something, So this is, if you really want that's the vision, that's the vision of Destination Earth, that's the vision of the digital twin. All right. So, a couple of examples about use cases, why it's important to go from the physics into society. When you have such a system that I showed on the previous slide, you want to be able to, they're not after me, you want to be able to go walk through climate information and pick out something. Does that move? Yeah, it does work. And you want to walk through climate simulations. You want to understand where at a certain point in my future climate the best spot would be for me to collect wind energy, for example, or solar energy. That's the kind of system you want to have. And then you play through it. You go everywhere, you change something, and you try again. You want to listen to data, just like to a podcast. It's just climate data, and then you want to play with applications like that. Or you want to say, how would an extreme event that I just experienced actually look in a future climate that's 4 degrees warmer? Would that extreme event be the same, or more extreme, or go away? And what does it mean at European scale, and what does it mean at local scale in Rome, for example? So this requires an entirely different information system that we have today. If you have a weather extremes example, so that's more days and weeks, you would like to look at the weather forecast, and you would say, okay, I'm interested in heat, or I'm interested in a windstorm that's just developing over there. I want to then tailor and fine-tune that system so that it provides me exactly the information I need, because I'm working for a wind energy company, and I need to manage my grid, or need to plan the change of the grid in 10 years. So this is the kind of chain and information system you want. And all of this, of course, at the speed of light. So we call this digital twins because of this interactivity and the integration of the social part and the physical part. And there's actually increasingly popularity of that thinking in our discipline, in Earth system science. And these are just a couple of examples of that. So it's something, and I'm going to come to that when I talk later about private companies. So of fundamental importance are better simulations, better models. I mentioned these deficiencies, the weaknesses, the small scales. So better simulations based on higher resolution are really, really important. You need to resolve clouds, you need to resolve convection, so three-dimensional motion in the atmosphere, sea ice, and ocean. That's something NVIDIA, the computing company, developed for us as an interactive system to, like a flight simulator, fly through the data. And spatial resolution is really important. This is, again, a couple of publications that were published in the last 2 or 3 years that really show small scales matter. So resolving the Gulf Stream and all the eddies that you have seen in the AMOC video before matter to the heat transport and the exchange of energy between atmosphere and ocean. It matters for precipitation, as I've mentioned. It matters for sea ice. So resolving these scales and the effect of the small scales on the large scales matter. There's one important problem with that, and that's the computational cost. If you increase resolution in your models by a factor of 2, so statement in the middle up there, computing roughly increases by a factor of 8. So if I want to go from today's operational global weather forecast, 10 kilometer resolution to 1 kilometer, where I resolve Rome, it's a cost of 1,000. It's 1,000 times more expensive to run this simulation. And that's a real issue. So what you see here, don't look at the details. We did actually an estimation of the computing cost of something like this on the biggest computer in Europe at the time, which was in Switzerland. So we ran a proper simulation model at full scale, and then we made an estimate of how fast we would need to be actually able to feed the digital twin with the computing. So we used the entire machine, very big computer, and our calculation was we need something like 20,000 GPUs and about 20 megawatts to power that system. So the computing scientists of you will know what GPUs are. The parents of you will know that as well, because your children's Xbox contains a GPU to do the quick image processing, okay? So you know that as well, and you're paying a lot of money for it. So 20 megawatts is about 20 million euros of electrical power cost a year. So that's important, you know? That's a big system to buy, and it's a very expensive system to run. So computing is increasingly in the center of our attention to make digital twins work. And we wrote a paper about this, again, 2 years ago, where we said, like, okay, what do we need to do in terms of more computing anyway, but in the way we compute our models and our forecasts to actually get there, to get that factor of 1,000. And there was a couple of solutions, and in the end we need, of course, very modern architectures like GPUs. We need to rewrite our entire codes. Not easy. For example, our ECMWF weather prediction model is about 2-3 million lines of code. There's an investment in mathematics, and there's, of course, machine learning. Machine learning for us in that context is very much a helper for accelerating the computing. Now, computing translates into data. So even if we had solved that computing problem and we could calculate our model predictions 1,000 times faster, we also have 1,000 times more data, and that's an issue. So this is a publication from some time ago. It's called the 6 V's of data. So you have more like the engineering part on the left-hand side. It's just more, it's more diverse, it comes in faster. And then you have the other V's, which are about what you do with the data, the value you create with the data. So these are the challenges. And what we expect in the future from the digital twins is probably production rates of 10 petabytes a day. That's a lot of data. And if you just want something, specific information extracted from that because you're, again, working for an electrical engineering company, then you have to apply a lot of computing again to extract that information. But of course, on the right-hand side, if we had that vision realized and the digital twin would work, there's infinite room for getting value, not just for society, but even economic value. Imagine the applications you could have if you had access to this kind of data and you are Google. Infinite money in there and business, but also benefit for society. So machine learning. Obviously, machine learning is everywhere. There's a lot of funding on machine learning. I'm sure 80% of it is wasted. But the other 20%, but it doesn't, you could say, okay, I've seen this before. The other 20% matter. So let's make sure that the 20% are invested right. So there's a lot of companies, of course, investing in it. Google, DeepMind, NVIDIA, Microsoft, they all do that. IBM does. And there's a lot of science around that for technical applications, but of course also for doing that important part of extracting relevant information from tens of petabytes of data per day, which is really, really important. So lots of potential. And the importance, I think, is in our community to make our domain knowledge benefit from that boost. A lot of people see this machine learning and Google as a threat. In our business, and I'm going to come to that, I would say thank you for showing us what's possible. You did that in 2 years, what would have taken us 10 years or 20 years, and now we take over. Now we're going along. So how we spotted but underestimated the potential of machine learning. 2 papers. One is this. When we look, ECMWF has now a machine learning program, so an internal program to work on machine learning, just about what I said. And this starts on the left-hand side with a paper that I wrote with a colleague like 5-6 years ago. And the motivation of that paper was actually started in an Irish pub at a computing conference. And I was talking to a guy from NVIDIA, and he said, don't you think we can do the entire weather forecast with machine learning? So not just a little problem, a sub-problem, but the whole thing. We just train with past knowledge of weather, our machine learning architecture, and then we run a model that's better than you. And I said, no way. So that was what that paper was about, and I think I was wrong. The second paper is again this. What that graph was trying to show is the potential of individual changes in our forecasting system and computing to achieve everything that's desirable on the outer surface of this hexagon. So if you are here, you have a very large contribution of something individual to that. And I think we underestimated what the machine learning box here says. I think the machine learning would have contributed actually a lot more to these individual things than what we thought only 2 years ago. So what happened in the meantime? In the last year, there was, in the weather business, and that's why that changes the economies of weather and climate, a number of publications from Google, Microsoft, NVIDIA, Huawei, a Chinese company, about machine learning applied to weather forecasting as a whole. They train, again, with past knowledge, they predict the weather. And again, you see scores here. So this is, again, this score curve I've shown you. And there's a couple of arrows up there that show where these machine learning models sit. And one of them, that's GraphCast, is better than everything in most scores that we actually calculate. That's frightening, but that's also encouraging, because it tells us that certain parts of our system we can make so much faster and so much better with the use of machine learning that will enable us actually to do exactly what we're missing, digital twin, faster, better, and more interactive. And the other curves basically show the same thing. Just the bottom right is something about tropical cyclone path prediction, where also the machine learning produces very, very good results. So that's not a threat in my case, in my interpretation. That's a real opportunity for us to do something, which led us to write a paper just in August about this changing economy, where we say, okay, the market has changed. There's there's private players like these big companies now. That's good. They invest a lot. They have an interest. They have a business. But let's just get together with them. Let's empower ourselves with the knowledge of machine learning and their expertise and do something together. It's really, don't keep them away. Don't consider them as competition. They are in a way. But, embrace it, swim with it, and try to be just that bit faster and better than them. That's what this is about. And I think this is really an opportunity for us and requires a lot of expertise that's actually in this room. So for me, to realize that information system, machine learning will be essential. Because without, you will not have the quality, the interactivity, and first and foremost, the speed to do all that interactive work. So that's really important. And private players do listen. So we at ECMWF have been working with NVIDIA, and the CEO of NVIDIA, Jensen Huang, is actually in the telcos. He wants to do something good. They do listen. They have a business idea, but they also want to help you. You know, some fly to space, some want to do something to climate. And they do. So they prepare hardware and software systems that can actually help us do that. So I think right now we're actually in a very, very good position to solve our problems. Is it worth it? I guess in this room, that's the wrong question to ask. You know, all of this is going to cost some money. It's going to cost probably hundreds of millions of computing and science. Doesn't matter, because the cost of climate change and extremes is trillions. In the very near future, trillions actually every year. So the benefit will be, of course, incomparable with that. So Destination Earth is that program I mentioned at the beginning. So to complete the digital twins, we estimated at the time 7 to 10 years. The first 2.5 years are almost over. It was 150 million for that. It will use, or is using, Euro HPC. Some of you in the audience know that, of course. These are the biggest European high-performance computers that we have. One is actually in Bologna, called Leonardo. There's 2 others, one in Spain and one in Finland. We're using all 3 of them, not to full capacity, but we have access to them. That comes in kind. And Destination Earth is being implemented by my previous employer, the European Space Agency and the European Agency for Meteorological Satellites. So it's a joint forces of European, again, thinking to address that issue. Interestingly, it's funded by DG Connect. So those people of you who are familiar with European funding, they have these DG, Directorate General. And there's a DG Climate, there's a DG Energy, there's a DG Research. So DG Connect is about digital technology. So they understood that at the core, so the heart that makes everything work is digital technology. Without it, no digital twin. Right. Let me skip that, because that's about, you know, how we do it, but it's probably too technical. But in the end, it's about, you know, running the best simulations, using the best observations, with the best computing and machine learning to realize these digital twins. So Destination Earth now has created something beyond Europe, which is called EVE. You know, EVE has a very positive connotation, but it stands for Earth Virtualization Engine, and is basically taking this digital twin idea to the global level, because Destination Earth is Europe. And some of the ironies in Europe is that you have a European Commission-funded activity, and the UK cannot benefit from it or contribute, or Switzerland cannot benefit or contribute to it, you know, and that's really ironic and cynical, because some of the best experts in science or computing science are from these countries, you know. Anyway, there's a lot of stories to tell. So, but what EVE is trying to do is to globalize that, you know. Think Destination Earth Europe, another Destination Earth in the US, another one in Africa, a third one in Asia, and join forces, you know. You specialize on machine learning, you specialize on the science part, you specialize on the societal aspect, and we bring everything together in a single system. And this is what this is about. So it's a lot of authors indicating, of course, microscopic contributions by most, but it's more a political message of, you know, the entire, or almost the entire European, you know, weather, climate, computational science, societal science, social science names are there. And it's about this. So it's about a tool, you know, it's a tool like this. You know, this without the internet is useless, it's just a phone. With the internet, entirely different story. This without very powerful processors is useless. This with what it has, you know, CPUs and GPUs in it, is extremely powerful. It's more than what we had when I did my PhD as a supercomputer, you know, in this phone. Amazing. And then you can build apps on it. You know, a digital twin can have apps. You know, it can have an app for a climate scientist, for a social scientist, for a company, for a politician, you know. And then the potential is unlimited. So this is what EVE is trying to realize at the global scale. So back to ChatGPT. So if you type into ChatGPT the questions I had at the beginning, this is what you get. You know, that's not good enough. Okay. So I leave that there, and thank you very much.